Welcome to lecture 4 of the PhotoTechEDU series. I'm Iain McClatchie. So today I'm going to be talking about contrast and what happens to your image on the way from the surfaces that you're photographing and the sensor that actually generates the image. So to do that, I'm going to have to talk a little bit about luminosity. I'm going to cheat a little bit there, you'll see in a second. Define contrast in terms of luminosity, and then the modulation transfer function is the way of describing what happens to contrast on the way to the sensor. And then I'll talk about one half of what happens to the modulation transfer function, which is flare. And then I'll try to motivate why we care about contrast at all by talking about noise. So luminance is defined as the light power coming from a surface per solid angle. What we're looking at here is a line of 11 boxes at gradations of 10%, a full range of what this projector can produce. And talking about it in terms of percentages is not the way you work when you're computing lumens or candelas or whatever coming out of actual surfaces and trying to count photons landing on the sensor. But for the purposes of doing math in your head and getting the general idea of how MTF functions work, percentages work pretty well. So I'm going to cheat, and for the rest of this talk, I'm going to talk about luminance in terms of percentages of full range. So, but to give you, before I really start cheating, to give you a better idea of what luminosity, how it's actually defined, your eyes are more sensitive, as I think Dick talked about in the first lecture, your eyes are more sensitive to wavelengths around green at 555 nanometers than they are to wavelengths either shorter or longer than that. And your total spectrum that you can see ranges from about 400 nanometers to about 700 nanometers. There's two curves here. The green one corresponds to your sensitivity to very dim light, and the black curve corresponds to your sensitivity to brighter light like what we're in right now. There's actually some debate about what the right curve is for that black curve, and so you can see on this slide a number of variations around 450 nanometers. These are actually defined by the CIE organization. So what these curves are trying to convey is that the same your perception of brightness for the same amount of power at different wavelengths, your perception of brightness is different. And so to get an overall value for luminosity, we basically do a weighted sum of the spectral power hitting your eye, weighted by one of these two curves, depending on whether we have bright light or not. And for practical purposes, we almost always use the dark curve here for estimating things about general purpose cameras.
Do you mean the curve that was drawn in dark, or the curve corresponding to seeing in dark?
Thank you. Yeah, the curve that's drawn in dark, not the curve that's drawn in green. The curve that's drawn in dark corresponding to light levels like what we have here. So just to sort of calibrate you for what we're going to see in a second, this is a 90% versus 10% alternating series of squares. So the way a modulation transfer function works is you can imagine you have a surface, and the surface might have a series of white and dark lines on it. A fairly bright white that you can get might reflect as much as 95 to 97% of the light hitting it. If it's a diffuse reflector, it's hard to get more than that. And your sort of white paint or whatever will generally get you about 90%. On the other hand, it's hard to get down to 0% reflection with blacks. And I believe you can get down below 10%, but in general, 10% and 90% are sort of close to the bounds on what you'll see in ordinary objects around you, black shirts, the floor, that kind of thing. And so the difference between those two is 80%. Light emitted from a surface on the left-hand side of this slide here goes through a lens and arrives at the sensor surface. And there, we've lost some contrast. The light areas have gotten darker, the dark areas have gotten lighter. And now we have about, the difference between the two is 40% of full range. 40% is half of 80%. The MTF here would be described as being at 50%. It's a little simple. MTF typically isn't specified as just one percentage. In fact, there's a number of different ways of specifying it. I'll show you what it actually is later on in the talk. It's somewhat complicated, so we always try to summarize it in some way because many of the complications of looking at it aren't necessary. So typically, MTF will be specified at different frequencies, spatial frequencies, at the sensor surface. So here I've made up two, 20 line pairs per millimeter and 40 line pairs per millimeter. A line pair per millimeter, 40 line pairs per millimeter would mean that you had 40 dark and 40 light alternating stripes in 1 millimeter. So that would mean that the individual stripes would be 12.5 millimeters wide. Once again, you can imagine we have this alternating pattern on the left. If the MTF at 20 line pairs per millimeter is pretty good, at maybe 90%, but it's rolled off, and by 40 line pairs per millimeter it's down to 50%, we'd get an image something like on the right. And you can see that the higher frequency bands have lost more contrast. So I want to motivate, lenses are typically quoted at, very often they're quoted at 10, 20, and 40 line pairs per millimeter. So I wanted to motivate you as to why that would be. Pictured here is a fairly typical full frame CCD. This would be used in a high-end digital SLR. Most digital SLRs do not have full frame sensors. They're a bit smaller, but this will serve as an example. So in this particular full frame sensor, it's, well, all of them, full frame means full frame for a 35 millimeter camera. That's a term of art, I suppose. So that means they're 36 millimeters wide, 24 millimeters high. The pixels on this one are 9 microns on a side. Sizes for pixels range from between 6 and 9 microns. So if you think about a set of 9 micron pixels covered with a panchromatic sensor that's not trying to capture color information, the highest frequency they can capture without aliasing would be alternating 9 micron stripes of dark and light on the sensor. The corresponding frequency would be 55 line pairs per millimeter. On a sensor that had smaller pixels, you'd have a higher frequency. For general purpose cameras, most of them have bare pattern filters on top of them. And as a result, what that means is they have alternating red, green, and blue filters over the pixels. And as a result, they patterns at 55 line pairs per millimeter, or whatever the pixel pitch is, would introduce color moire. And so to avoid that, they sometimes have anti-aliasing filters. But in general, they're not interested in frequency much above about 1.8 times less than their pixel pitch. So what that means for this guy is about 30 line pairs per millimeter. And so that's why you see these things quoted at 10, 20, 40 line pairs per millimeter for a particular lens. You can read the fall off of sharpness from there and get an idea of what that's going to mean for a particular sensor that this thing might be dropping an image onto. So I thought I'd show you some measured MTF curves. These are two from a website called photodo.com. It's a real asset. So the man behind this website measured several hundred lenses over the course of about 20 years and put them all on the web so you can compare and contrast them. So this is a very good lens. I haven't owned this lens. And so how do we read this chart here? What is MTF? So if we look on the left-hand side, at the lower left-hand corner of the chart, it says 90/8. That means it's a 90 millimeter lens, and he's stopped it down to a relative aperture of f8. And you can see 3 solid red lines and 3 dashed red lines on the chart. Solid red lines correspond, I believe, to sagittal MTF, and the dashed red lines correspond to tangential MTF. And from top to bottom, they are at 10, 20, and 40 line pairs per millimeter. And that's true of all his charts and also most industry standard charts. So I should explain the difference between sagittal and tangential MTF. The amount of blurriness that a lens exhibits is different in the direction towards and away from the center, the optical axis of the lens, and tangential to the optical axis. And so they actually measure them separately. And you can see they behave differently on these charts. The other thing you can see on these charts from left to right, you see these numbers at the bottom if you have really good eyes in the back, going from 0 to 21. If you remember, that full frame sensor was 36 by 24 millimeters. So it's 42 millimeters diagonal. So from the center to the farthest corner is 21 millimeters. And the way these lenses are rated, this is also a typical way of presenting a summary of MTF, is they're rated for the blurriness of the lens produces as you travel from the center of the optical axis out towards where it intersects the image sensor out towards the corner. And so this lens is typical of most lenses. You can see on the right-hand side that it's blurrier in the corners than it is in the center. And you can see that it's blurrier at higher line pair per millimeter frequencies than it is at lower ones. There's 2 charts here. On the left, I said it was a relative aperture of f8. And on the right, it has a relative aperture of 2.8, which is much wider. Yes?
So you're saying blurriness, and I wonder, does that mean that essentially all of the MTF loss comes from blur, or is there significant? I mean, I've had a lens where I thought it almost all came from scatter inside the lens because it was sharp but flat.
Thank you. What Ram covered in the previous lecture was loss of MTF, blurriness due to aberrations, and I guess it's lack of stigmatism in the lens. And what I'm going to cover in the later part of this talk is going to be flare, which is exactly what you're talking about. And I have a slide coming up which will sort of try to show the difference between the two. Yeah?
So just to clarify for me, you said the center of the lens versus further away, but of course when you stop down the lens, like to f8, or even when we went further, we really are only using areas near the center, yet we see it falls off even more drastically at f8 than at f2a.
That's a good question. So when we talk about the center of the lens, there's a number of points along that optical axis. So when you stop it down, you're using you're cutting the light to use a smaller aperture through the aperture stop of the lens, which is somewhere in the middle. The light projected onto the image plane, there's less light, but it's still projecting over the entire image plane. I'm not sure if that answers your question. The radii listed at the bottom of this chart are on the image plane, not at the aperture.
Right. So in other words, what I was guessing you're going to say, but so the issue becomes the fact that it's not going as parallel or whatever to the image plane, but the light is coming from the center of the lens to the side of the sensor.
Can you repeat the question?
Yes. So the question really has to do with what stopping down a lens really means. And the questioner is trying to so if you imagine that there was an optical element just ahead of the aperture stop in the lens, then as you stop it down, as you say, you would use less of the periphery of that optical element and more, and you would be left with only the light going through the optical axis at that optical element. That's not true of optical elements at, say, the front and back of the lens. In particular, near the front of the lens, all of the rays that go to one point, say, in the corner of the image, may pass through only a small portion of the front element of the lens. And you can see this. If you take a lens and you take it off the camera and you open up the aperture and you look in the front of it, you can see the entrance pupil. And what you'll notice is that the entrance pupil isn't covering the entire element, that entire front element. So if you were to cover some portion of that front element, you would not be occluding any light going between your eye and the, whatever it was getting projected to in the image plane. And that sort of highlights the difference between stopping down at the aperture stop of the lens versus making what I think is called a field cut in the image plane. So once again, these radii are referring to the image plane, which is not reduced when you stop down the lens. Please.
For this F8, you noticed that it was kind of bad toward the corners. That's usually the opposite of what we expect. Can you explain sort of why that might be?
I see. So the questioner points out that it appears that MTF is dropping off as we get to farther radius from the center of the image, and that's different than what you expect.
Well, versus the 2.8, it seems worse than I would expect between F8 and F2.8.
I see. Your point is, what you're getting at is that, yes. So your point is that when you stop down a lens, you would expect it to become sharper. And so what you would expect is that on the F2.8 graph on the right, that all the lines would be higher than the ones on the left. Right. So when you stop down a lens, the benefit that you have is that you're using less of the glass in your optical elements, and you're subject to fewer of the aberrations in those glass elements. On the other hand, you're more subject to diffraction. And so this gets into difficulties in lens design that I'm not really qualified to talk about, but essentially you don't always get what you expect, and stopping down often can make things worse in some areas. Although, as you say, in general, stopping down a lens will make usually makes the overall lens sharper until you get to a diffraction limit. And the diffraction limit for most lenses is around f8. And once you start stopping down more than that, usually there's very little difference between f8 and f11, but past that you start getting into noticeable diffraction effects. Yeah, Francesco.
Those curves falls along the same explanation. I mean, there is a meaning.
Yeah. Yeah, absolutely. This has to do with the if we were to treat this lens as a telescope, and we were to look at stars, and we were to look at the projection of those stars onto the image plane, we would get something called a point spread function, and I'll get to that in a slide in a moment. And that point spread function will change shape as we get to different parts of the image, and you can get these minima from the different ways that it changes shape. That's not a very good answer. Wait till I get to the point spread function slide, and hopefully it'll answer your question a little bit better. So the thing that I wanted to show between this slide and the next slide is that this is a $500 lens, and this is a $4,600 lens. This is the sharpest lens that the guy who did all this testing has ever tested. It's the Canon 200 millimeter 1.8L. It's actually not manufactured anymore, and I don't know why. I suspect actually it has something to do with difficulties in manufacturing. So it's interesting in that at f1.8, it is almost as sharp as it is at f8, and it has very little drop-off towards the edges, which is a pretty magnificent achievement by the designers. So the sort of takeaway from this slide is that getting significant improvements in MTF costs really vast amounts of money. And so this is why typically lenses are specified at 50% MTF, which is probably the largest loss of MTF in the whole system of getting light off the surface through the lens onto the sensor. There's actually an MTF associated with the sensor itself due to crosstalk between pixels. But by far the largest loss is in the lens. And the reason for that is that it's so expensive to do better than 50 or 60%. Yeah.
Excuse me. Were all these tests conducted assuming essentially a flat black sensor, or were these realistic sensors?
Thank you. I'll be getting to that in a moment. And they were all conducted assuming a flat black sensor, which underestimates the amount of flare that would be in the lens, and therefore overestimates the MTF, especially at low frequencies. Yep.
Do you know the exact characteristics of the MTF? Can you reverse it later?
So it's a very good question. If you know the blur function of the lens, can you reverse it later? The usual name for doing that kind of thing is deconvolution. And the reason people use the word deconvolution is because they like to summarize the blurriness of the lens as a point spread function that is convolved with some ideal image. The difficulty with that is that the point spread function changes depending on where in the image field you are. And so it's not a linear transform. Deconvolution would be, and would actually be relatively cheap. So there's sort of two problems with deconvolution. One of them is the one I just said, and the other one is that when you deconvolve, let's see. When you deconvolve, you amplify the noise that you have. It's the same as any other signal processing. If you try to reduce intersymbol interference, you end up increasing noise. No.
Do it if it was band limited. After that, all you're doing is amplifying high frequencies, sharpening. So you can do sharpening, but if there's any other high frequency information there, for example, you're seeing that a bunch of sharp edges in it, then you're going to add noise.
So
that aliasing is going to come back. You can't, in principle, do deconvolution.
right. So Chris points out that with a sensor like a CCD, you're essentially doing a sampling in space, and you're going to get aliasing at higher frequencies than the frequency at which you sample, or half the frequency at which you sample. But the practical difficulty here is that, and so Chris's point is that if you could band limit your output to have no frequencies above the Nyquist limit, then in principle you could amplify you could deconvolve your image. And the practical difficulty is that the noise process isn't easily separable from the data acquisition, and so you you will get noise even below the Nyquist frequency, and when you amplify to deconvolve, you will amplify that noise even if you manage to band limit the noise above the Nyquist frequency. Yes. I don't have a graph, and I haven't seen a graph. My understanding is that it's quite adaptable, so that it's fairly poor at the edges and very good in the middle, But of course, you keep moving your eyeball around to get the good part and whatever it is that you're interested in. And this is sort of a fundamental difference between what cameras have to do and what the eyeball does, right? Because it's part of your experience that you get to move your eyeball, and the camera doesn't get to do that. Yes?
So cheaper cameras have smaller sensors, it's probably good from the point of view of the graph, but also presumably smaller pixels, it's probably bad. Do those two effects cancel each other out into roughly the same shape of the graph?
Yeah. So that's basically the last slide in my talk, and now I think you guys have predicted almost the entire rest of my talk. So if you don't mind, I'll just flip through it and get to all your questions. So here's the point spread function that we were talking about. So this is actually a shot of, I forgot the name of the star, but it's a small isolated star that was shot by the Spitzer Space Telescope. And what we're looking at, and what you can't see too well on this projector because it has lower dynamic range than my screen, is that you have a sort of a bright central area, and then the rest of the image has also got some brightness to it, but not a lot. And so the central bright area, and you can see the shape of it, it's a bit taller than it is wide. That's due to the aberrations in the lens itself and the optical train, including the reflector. And then the sort of diffuse and uneven glow all around it is due to internal reflections inside the lens itself. And so the point spread function has sort of this central area, which the point spread function is the Fourier transform of the what's actually called the OTF, which is the optical transfer function. MTF is the amplitude of the OTF. There's also the phase. But essentially, the central point, it's a Fourier transform. So the central point of the point spread function corresponds to the high frequency portion of the MTF curve, and the broad tail, the broad surround of the point spread function corresponds to the low frequency portions of the MTF graph. And that's why it is that lens flare is responsible for loss of MTF at low frequencies. So Ram ably talked a little bit about the aberrations last time, so I'm going to get into flare here. So first, why do we have any flare at all? It's because light reflects off of changes in the index of refraction of the materials that it's going through. This is like any other wave. You know, if you have electrical waves moving through wires and you have an impedance mismatch, you get reflections off that too. Exactly the same thing is happening here. And the reflection is based on the difference in the indexes of refraction. Glass has an index of refraction about 1.5, and air is about 1. And so if you take the difference, you get about 4%. And so when you look in the window of a house during the daytime, and you see that you can't see into the house very well, it's because you're getting 4% reflection off of both surfaces. About 8% reflection of the exterior scene is coming off that glass, and then overlaid on top of that, or superposed, I guess is the right way to say it, you have the image from the interior of the house. This is why it's difficult to look into houses, because the house would have to be at least 12% as bright as the exterior in order for you to even get, you know, a one-to-one signal to, not noise, but interference. And it's very unusual for interiors to be that bright. So in the early part of the 20th century, this reflection off of glass surfaces made it completely impractical to have many element lenses. So they would typically have lenses with say 6 elements cemented into 2 groups. So there's only 4 air glass interfaces, and even that was even lenses like that would exhibit fairly draconian amounts of flare. And towards the middle of the 20th century, they developed this wonderful technology of coatings, which, to a first approximation, almost eliminated the problem. Certainly, as Jim was pointing out, if you measure the flare of the lens without having a sensor behind it, things look pretty good. So the simplest kind of coating is if you were to coat the glass with a coating that was 1/4 wavelength thick. So that would be around like 120 nanometers thick, or 140 nanometers, something like that, and you were to coat it with something that had an index of refraction, which was the geometric mean of glass and air, then you would get these two reflections, and they would be 2 times a quarter wave or a half wave apart, and they would be equal in intensity, and so they would cancel, and you get nothing. That's going to vary as you get off frequency, and it's also going to vary as you change the incident angle to the glass surface. And both of those complications are responsible for a fair bit of the flare that you see in, say, eyeglasses, which usually have fairly simple coatings. The other problem is that there really isn't a good material with an index of refraction at the geometric mean, which is 1.38. The most commonly used material is magnesium fluoride, which has an index of refraction of 1.23. It's a great material. It's nice and hard, but it doesn't get rid of all the reflection. And a single quarter wave coat of magnesium fluoride leaves you with about 1% reflection, which is a lot better than 4. So if you go to a coating house and you ask them, well, what can be done? The answer is lots and lots. So these are 2 graphs. Once again, you would need good eyesight, I guess, to read the labels. So the vertical axis is percentage reflection, and the graphs are going from 0 at the bottom to the top of the left-hand graph is at 4%. And I've scaled the graphs so that they match that way. And the horizontal axis is essentially 400 to 750 nanometers. It's a little bit more than the spectrum of visible light that you're sensitive to with your eye. And so what's interesting is on the left we have a graph of a standard 3-layer coating, not a 1-layer coating. I'm told these 3-layer coatings are quarter, half, quarter wave coatings of different index of refraction materials, and you can see that they get below 0.5% of reflectivity. And on the right is an optimized coating. It's 4 layers thick, and it's been optimized to the index of refraction of the underlying glass. Glasses vary in index of refraction, I think it's around like 1.48 to like 1.59, somewhere in there. And so by actually changing the material stack and the thicknesses to account for that, you can do even better. And on the right, we have a coating with, over most of the range, it's reflecting less than 0.1% of the incident light. This is 40 times better than you'd get with regular glass. It's a huge improvement. And so the net result is that coatings like this made it possible. There were sort of 2 things that revolutionized lens design in the 20th century. One was coatings like this, and the other was, it was less of an effect actually, was computers that could run simulations of rays being diffracted through the lens and help the lens designers try more complicated lenses. Yes? Oh yeah, they're a huge thing, because by reducing the amount of reflected light inside the stack of lenses that you're looking through, they're reducing the amount of flare. Without these coatings, you would be lucky to get even 20% or 15% MTF at any frequency through any common lens you care to name for a modern camera.
So historically, there was always a lack of coating on polarized filters until like the last 15 years or so.
Yeah.
Was that just a manufacturing coating issue process, or?
I would imagine so, but I don't know. Yes?
Is there such a thing as a gradient for the optical index? You might have very, very low reflection for that gradient.
I see. So I have read of such things. What they do is they deposit a material with an index of refraction of, let's say, 1.2 onto an underlying substrate of index of refraction 1.5, and then they heat the 2 up so that the 2 diffuse through each other, and you do get a gradient that I know that's not used for anti-reflective coatings. The anti-reflective coatings that I know about rely on cancellation, and the thing that you're talking about would rely on essentially not making a sharp transfer, so you get very low reflectivity at any given depth. I think the problem with things like that, though, is you'd have to find some material that was very close to air in index of refraction. And I think that's the sticky point.
We're working on the air.
Yes. Well, actually, we are, right? So there's a problem with the best lenses in use today are used in semiconductor manufacturing. And the problem that they have with the 45 nanometer production node is that they can no longer get their 193 nanometer laser light to focus down to produce structures that are 45 nanometers in size. And the problem is the air, and so they're getting rid of the air and they're replacing it with other stuff that has higher index of refraction and therefore actually gets the 193 nanometer light to become effectively shorter wavelength inside that material, the liquid. And therefore you get, you're better able to image smaller structures. So this is the coating part of the problem. So as Jim was pointing out, the big problem in all this is the sensor. The sensor is vastly more reflective than the glass surfaces. And my understanding is that CCD reflectors are differently reflective than film. They may be somewhat, they're about the same reflectivity, I think, overall, but the problem is that CCDs are more specular than film, which was more diffusive. And as a result, film would tend to reflect more of the incoming light into the baffles or whatever it is at the edge of the sensor cell that absorbs light. And CCDs tend to reflect it right back into the lens stack. Yeah, Lance?
Is it practical to apply coatings to the sensor lenses as well?
I think that's the next slide. It is. It's the next slide. Okay. So it's not, or it is only in some cases, and that's the bottom of the slide. So, so here's the problem with the sensor reflectivity. The index of refraction of silicon dioxide is about 1.5, and for silicon it's about 3. And so the reflection off this interface is 11%. Now, for most of the sensors that anyone here could afford, you are, the collection surface through which the light enters the sensor is the active surface of the chip. So you have, you're fabricating transistors on this same surface. The semiconductor people are completely unwilling to allow you to do anything to that surface at all. There's going to be no magnesium fluoride probably in that part of the fab. It's out of bounds. So there is no one that I know of seriously proposing to do any kind of coatings at all on that part of the sensor. That said, there's something called a backside thinned CCD. And the way this works is that you grind the chip very thin, so on the order of, I think like 15 microns thick. And then you have to do different dopant profiles, but essentially you use the backside of the sensor to collect the photons, not the front side. And this has a number of wonderful advantages, one of which is you can coat the backside, so you can make it anti-reflective. Another wonderful property that it has is that since you don't have any wires on the backside, you can use nearly the whole area of the chip as light gathering area, and you avoid many of the problems that front side sensors have. The biggest problem that front side sensors have, and this especially shows up in more modern sensors with smaller pixels, is that as you scale the pixel down, the thing that scales down best is the photodiode, which is the part that's getting the light. The stuff that scales down less well is the wires that are taking the information out of the pixel and getting it to the periphery of the chip where you can process it. And so what tends to happen is that your fill factor, the percentage of the front of the chip that actually manages to absorb light, is going down as you make your sensors smaller. And this is only making the problem of having fewer electrons worse. So this is one of the reasons why when you look at a cell phone picture or something like that, you see really astonishing amounts of noise. It's because those sensors essentially count individual photons coming into the lens. They do. Even in reasonable amounts of light, they do. So the reflection off the silicon to silicon dioxide interface is about 11%. The Bayer filters on most of the sensors, on color sensors, are absorbing quite a bit of light coming down to the sensor, and then of course they absorb a bit more on the way back up again. And so they reduce that 11% a bit, but on the other hand, you have usually indium tin oxide and aluminum wires on the surface of the pixel, and those are quite bright, and so those reflect a bit more. And so the overall reflectivity ends up being somewhere in the range of 10%, and this varies by a fair bit from one manufacturer to another. So, and like I said, no AR coatings on the active surface. Backside thin CCDs are used primarily, that I know of, in very expensive security cameras and in astronomy telescopes. So it gets worse. So not only do we have a sensor back there, but we usually have an IR cut filter. So the issue here is that the dyes that these little spots of dye that sit in front of the pixels that color them red, green, and blue don't absorb infrared or ultraviolet light. Ultraviolet light is a little bit of a problem. Generally, the glass in the lens stack itself is absorbing some of that for you. A much bigger problem is infrared. For instance, I believe it was Leica's M8 that just came out. They, I don't know exactly what happened, but the infrared cut filter had the wrong cutoff frequency. And as a result, wedding photographers started noticing that women wearing black velvet, which is a synthetic fabric, tends to be fairly bright in infrared. And these poor women look like they're wearing purple velvet instead of black velvet. And so Leica has now issued some sort of program that's, one of these typical corporate responses to a problem like this. They will give you 2 infrared cut filters that you can screw onto the front of your lens, but not more than that. There's all kinds of, it's a lot of accounting headache for making an engineering mistake. And presumably they've fixed the IR cut filter in their cameras they're selling now. So the problem with these IR cut filters is that there's a number of different ways of building them, but one good way is to use stacks of material like those broadband anti-reflective coatings that I showed earlier. But instead of using 4 materials stacked, these typically use like 25 to 30. And sometimes they might have both sides of this, what's called a plano-plano element, very thin piece of glass usually. So they're fairly complicated coatings. And what they're trying to do is instead of they're trying to be extremely reflective in the infrared and then be less reflective in the visible wavelengths, whereas an anti-reflective coating is trying to be not reflective in the visible wavelengths. So the problem, what ends up happening is that you can't get an infrared cut filter, what's called the dichroic infrared cut filter. That's the stacks of materials coated on. You can't get one that has anything like 1% or less reflection in the visible band. What you can get is maybe 2% or more likely 4%, and that's fairly reflective. And so you combine this with the sensor at the back, and you have this really great path for sending light in and then sending another image of it back onto the sensor.
Is this separated from a sensor usually like that, or is it right on top of a sensor?
I think that's the next slide. It is. So the question is, where do you put this IR cut filter? So if you're making an SLR, a digital SLR, and you want to be compatible with a line of lenses going back 30 years or more, which is what many digital SLR manufacturers, that's the position they're in, you can't assume that the lens has the IR cut filter in it. You could propose that somebody put an IR cut filter in the front of the lens, and the problem with that is that these coated filters change their cutoff frequency depending on the angle of the light going through them. And so for a wide angle lens, that's not a very good strategy because the angle of the light coming through the front element of the lens will change quite rapidly as you go from one side of the field to the other. Yes, Lance?
I've read that iron optical glass is what principally cuts off the ultraviolet method to it. What's the downside of flashing elements with gold or putting a little gold in the glass to absorb infrared?
So the question is, why not put gold or some other dopant in the glass to cause it to absorb the infrared? The answer is I don't really know. There are glasses that absorb infrared, and sometimes infrared cut filters are made out of absorbing glasses. The glass that tends to absorb infrared has the problem that it's not very good optically, and so having thick sections of it tends to introduce a lot of aberration, sort of nasty aberrations that you can't really grind out or come up with a surface for. So typically glasses like that are handled in very thin plano-plano sections, and that's it. Yes?
So if you're not taking wide angle, is it okay to put the IR at the front of the lens?
Yeah, actually it's a really good solution for a telephoto lens to put an IR cut filter in the front, because the angle isn't changing very much. It keeps the advantage to it is that it keeps the IR cut filter, it keeps this reflective surface far away from the sensor, and as a result, which I think is coming up in a moment, the total amount of light reflected back to the sensor is lower, which is what you want. So you could put the IR cut filter in the front of the lens, good solution for a telephoto. You can put it between the lens and the sensor, which is what you typically do if you're building a digital SLR, because you build it once, you put it in there, you're done. And the problem with that is you get this strong reflection, and so you have to work hard on getting a good coating to get that down to 2%, and then you need to also work hard on your software stack that estimates how much flare there is and where it is and subtracts it. And then the final thing you can do is you can do something somewhat like what Lance was suggesting. You can, but rather than doping the internal lens elements, you can coat them. Oftentimes you can find lens elements over which there isn't much sweep of the chief rays going through the lens relative to the surface that they're going through. Those are good surfaces to coat. The trouble here is that coating these glasses can be difficult, and there are yield losses associated with that, and so it drives up the cost of making the lens. But it has been done, and I actually think that most consumer point-and-shoot cameras actually use this technique to reduce flare. Many also have an IR cut filter in the back. There's a lot of variation in that space. So I wanted to fairly briefly go over why the geometry of the back of the lens, how the geometry of the back of the lens affects flare. So normally light passes from the left-hand side of the diagram that you're looking at to the right. So I've flipped this around. So my light is passing from the right to the left here. I've got a mirror here, which is actually going to be the surface of one of my lenses. I've got this object on the right-hand side, which is actually going to be the sensor itself. And I've got an image on the left-hand side here, which is the image of the sensor in the reflection made by the surface of one of the lens elements. So if you imagine that lens surface is convex, then you get this itty-bitty image of the sensor, and as a result, when you have light from the sensor emitting back towards the front of the lens, a small portion of that light will actually hit the secondary virtual image of the sensor, and the rest of it will be dumped into the baffles in the sensor cell. This is a good thing. So, you know, the rule here is that convex elements pointed towards the sensor in the back don't reflect so much light back to the sensor. On the other hand, if you have a concave mirror, you have the opposite effect. You magnify the image of the sensor, and as a result, the amount of light that's reflected back to the sensor is primarily a function of the exit pupil of the aperture of that concave element, and not so much a function of its distance away from the sensor. The upshot is that these concave elements reflect about 5 times as much light. That's a very rough approximation. It depends on the exact geometry, but it's about 5 times worse than concave elements, and or concave surfaces. And so this is one reason why when you look at the back of high-quality lenses, you'll see that there's a heck of a lot more convex surfaces than concave pointing back towards the sensor. So let me wrap up here. So far the talk has been about contrast and why you lose it. And now I want to motivate why you would actually want contrast. So I'm not sure if I judged this right. So the idea is that you can read most of these numbers, but not all of them. Basically, you have 20, it's 80, 60, 40, and 20% contrast. So 20% contrast seems like you can at least see the lines okay. So why do you need more than that? Why wouldn't we accept lenses with 20% MTF? And the answer is noise. The interesting, in many signal processing systems, the figure of merit that you use is signal to noise, and in photography, the signal is generally contrast, and the noise is photon shot noise. I'll cover that in a second. So, as an example of how much I want to motivate how much contrast you need to be able to see through noise. So I've got I've got some text here, and what I've tried to show is that if the text is large, like on the right, then so we have equal noise across the entire image here. But we have less contrast on the lower lines, on the lines towards the bottom of the slide. We have higher contrast in the lines towards the top, and the text is smaller on the left. So the idea is that on the right, or all the way across the top, actually, you can read all that text because you have high contrast. And so the contrast is better than the, significantly larger than the noise, and so you can pick out the shape. As we go down, you have, the bottom line has contrast, which is approximately the same as the RMS noise. And you can still read on the right-hand side because you have a very low frequency shape that you're trying to recover. As you try to pick up higher and higher frequencies, you need better contrast. You need better signal to noise at higher frequencies to recover the signal. So what this means is that if you're shooting small text, like some companies I know, the sort of root mean square contrast that you need from your image has to exceed the root mean square noise by about a factor of 4 for a sort of visually acceptable result. Now, so what I want to do now is back reference that to the noise process that you actually see. If we have black text on a white background, we might have about 80% contrast in the scene. That's a 90% reflective white and a 10% reflective black. If the lens MTF is about 50% at whatever frequency corresponds to this small text, then what we're going to end up with on the sensor is going to be about 40% of the full white response in contrast. The required signal-to-noise ratio was 4:1, and so that means that 1/4 of that 40%, or 10% of the white, we have to have noise, the SNR noise, sorry, the RMS noise has to be around 10% or less of the full range white response. Now, there's a reason why I've said it that way, and that's because, and this is my last slide, the dominant noise source in modern cameras is photon shot noise. I think Dick is going to talk about this in a later lecture, but in summary, the readout noise on modern sensors is so low that for pictures of acceptable image quality with low enough noise, you're not really looking at readout noise in a modern point-and-shoot camera or a pretty good SLR, digital SLR. Instead, what you're looking at is the photon shot noise. And essentially what's happening here is the photons come in, some fraction of them make electrons in the photodiodes that get collected, and there's I think it's a Poisson process associated with collecting those electrons, and you get noise, which is the square root of the number of electrons. So what that means is that if you need a noise to white level ratio greater than, if you need a white level to noise ratio greater than 10, you're going to need to collect at least 100 electrons per well to get that level, and that sets the low light limit of the camera. It also, because, and this gets back to, I've forgotten which person asked the question, but essentially, as we get newer sensors, the sensors have smaller pixels because that makes them cheaper to produce. but smaller pixels behind the same lens capture less light. You have less electrons. You have a smaller signal-to-noise ratio, and so the overall image looks worse. And this is essentially the limit on camera resolution. And it's an interesting limit because we're almost up against physics. The readout noise levels, for instance, in a Canon 5D, or for that matter, any one of the Canon point-and-shoots, the 8 megapixel point-and-shoots, they're all about three electrons of readout noise. And you can see that you need 100 electrons to cover just the signal-to-noise for this process. So the 3 electrons of readout noise is not significant. And so essentially, they could make it 0, and it wouldn't improve things very much. And so what's left is to get more electrons, and you're either going to need more glass out front with bigger holes in it to get the light through, or you're going to need a higher efficiency sensor. And sensor quantum efficiencies are already in the 40% range. So there's a factor of 2.5 to get there, and then you're done. Yes?
Is there a significant difference between CCD and CMOS sensors when it comes to noise?
No, not anymore. There used to be, and CMOS got a lot better. And so recently, actually, the CMOS sensors are very slightly ahead. But I would imagine that doesn't have anything to do with fundamentally CMOS versus CCD, and I suspect it has more to do with the amount of money spent on trying to make CMOS sensors work versus CCD. So this sort of motivates the talk to come on sensor noise and how those statistics work. Are there any questions? Yes?
So, one issue I have, especially with prime lenses, the more expensive the lens, the worse it is ghosting, which is a second, anytime you have a bright object in a dark scene, you get a second image 180 degrees opposite.
That's right. So what you're looking at is the reflection of the, let's say you don't follow the directions and you point the sensor into the sun, or you point the camera into the sun. You're going to get a picture of the sun on one part of your image. That image of the sun is going to reflect off the sensor, back off the infrared cut filter, and back onto the sensor again. And it won't quite be in focus. It's going to be somewhat out of focus, but you'll be able to see it. Another thing that will happen is it will reflect up through the stack of lenses and reflect back down again. And usually it'll be cut off by the aperture stop. And you can tell this is all called structural flare. And if you look at structural flare, you can see that some of them are kind of round, and images of the sun, and some of them are usually like 9-sided polyhedra. And what you're looking at is an image of the open shutter, or the aperture stop on the lens, from reflections off of surfaces in front of the aperture stop.
I know what you mean. You get these various polygons, but no, this is different. This is like at night you're shooting a cityscape. You get a building over here. You get a second image of it upside down. If you rotate it the convex 180 degrees, you get an exact image on the other side of the frame.
Yeah.
And this is both with film and digital.
So I don't have experience with that exact effect. So I would imagine it's probably very lens dependent. So I'm not sure I have a good explanation for you.
It happens on every lens, but the more expensive the lens, the worse it is.
That could be because your more expensive lenses generally have more surfaces to reflect off of. Are there other questions? No? All right. Thank you.